Welcome to the Deep Dive, where we take your sources, plunge into the details, and surface with the fascinating insights you need to know.
It's all about distilling complex information down to its most important and often surprising core.
Absolutely. And today, we are diving into a realm that feels both incredibly simple and, well, deeply mysterious.
Yeah.
The world of prime numbers.
Ah, yes, primes.
You know, those indivisible building blocks of arithmetic numbers like 2, 3, 5, 7, 11. So simple to define. But predicting where they show up among all the integers, that's one of mathematics' most enduring puzzles.
It really is. They appear in a sequence that seems, well, irregular, almost random if you just glance at it.
Right.
But mathematicians have discovered there's this profound underlying structure. It's not random at all, not really.
Okay, and our sources for this deep dive explore exactly that structure. We're pulling from excerpts of a book on prime number distribution, covers classical ideas, modern tools.
And we also have some discussions, I think, from online forums about recent, really groundbreaking work by Zhang.
Yeah, tackling problems tied directly to how these primes are spread out.
So these sources, they give us a kind of window into the cutting edge, how mathematicians are thinking about this stuff right now.
Our mission, then, in this deep dive, is to sort of understand the main techniques mathematicians use to study where primes pop up, especially when you look at them over shorter stretches of numbers.
Right, not just the big picture average.
Exactly. We want to highlight the big, challenging questions they're grappling with and see how recent progress, like the Zhang work we mentioned, fits into this long-standing quest. Okay. Let's unpack this mystery.
Sounds good. So at the heart of it all, really, is this fundamental question. Just how many primes are there up to any given number? Let's call it x.
Right.
Mathematicians have a notation for this. It's pag(x), the prime counting function.
And for centuries, watching primes appear, it must have felt like watching lightning strike. Just, unpredictable.
It certainly seemed that way. But a key insight came much earlier than you might think from Gauss. Late 18th century.
Gauss, okay.
He noticed that the density of primes around a large number x seemed to be roughly $1 log on.
Huh. Meaning, like, if you look at numbers around a million, about 1 in every, log of a million?
Yeah.
Numbers would be prime, roughly.
Precisely. Yeah, that's the intuition.
Mm-hmm.
And this observation, it led to the formulation of the prime number theorem.
The big one.
The big one. It states that as x gets very, very large, pi is very closely approximated by 610 numbers.
And this wasn't just a guess forever, right? It got proven.
Oh, yeah, rigorously proven.
Yeah.
Independently by Hadamard and de la Vallée-Poussin in 1896. So it's solid.
Okay, that feels like the first really big piece of the puzzle. While individual primes look kind of random, their average density follows this surprisingly simple, predictable rule. The prime number theorem captures that.
Exactly. And that theorem is incredibly powerful, no doubt. But it tells you about the average behavior over really large ranges.
Right.
To get a handle on the apparent randomness over shorter ranges, mathematicians also considered a probabilistic view. There was this notable idea from Kramer back in the 1930s.
Kramer's model, I think the sources called it?
Yeah. He suggested modeling primes as if they were determined by, like, a sequence of random coin flips, weighted appropriately, of course, based on that $1 log S density.
So you're saying primes might behave, statistically at least, like random numbers with a specific probability?
In some ways, yes. Statistically, this kind of model, it intuitively suggests that patterns we see, like twin primes.
Oh, like 11 and 13 or 17 and 19, primes just 2 apart.
Exactly those. The model suggests they should appear pretty frequently. It even gives a heuristic reason to guess there are infinitely many such pairs, the famous twin prime conjecture.
Ah, okay. So the random model gives you a kind of justification, or at least a strong hint, for things like the twin prime conjecture.
It offers a heuristic, yeah. A way to guess these patterns should exist. However, and this is critical, the sources highlight it, real primes aren't truly random. They have what are called local obstructions.
Local obstructions. Okay, what does that mean in plain English?
It just means certain patterns are simply impossible because of basic arithmetic. Like, other than the pair, 2, 3, you can't have 2 consecutive numbers that are both prime.
Because one must be even, right? And bigger than 2.
Exactly. Even and bigger than 2, so not prime. Another example the sources mention. For any number n greater than 3, the pair n to n plus 22 cannot both be prime.
Really? Why is that?
It's not super deep. One of them has to be divisible by 3. You could just check the possibilities for n modulo 3. It always works out that way.
Huh. Okay, I get it. So these are simple, like necessary arithmetic rules that a purely random coin flip model wouldn't automatically respect?
Precisely. So that's a second key insight. Maybe while primes might show this pseudorandomness, their distribution is heavily constrained by these unavoidable arithmetic properties.
Right.
And proving that primes do behave in this pseudorandom way, while also respecting these local rules and finding them in specific setups like arithmetic progressions. Well, it's called a holy grail in analytic number theory.
So how do mathematicians actually start trying to count or find primes, given these constraints? Where did the tools come from? The sources mentioned going back to early methods like the Sieve of Eratosthenes.
Yeah, the Sieve Eratosthenes Legendre. It's a foundational idea. It's basically a method for counting numbers up to x that are not divisible by any prime in a given set. Numbers co-prime to some number m.
Like filtering out all the multiples of 2, 3, and 5 to find numbers whose only prime factors could be 7 or larger.
Exactly that. The core idea is inclusion-exclusion. You start with x numbers, subtract the multiples of the primes, add back the multiples of pairs of primes you subtracted twice, subtract the triples, and so on.
Okay.
The formula reflects this. It looks like x times the product term, prod, 1p, over the primes dividing m, plus an error term.
And the source gives that error term as omega?
What's omega m? Is just the number of distinct prime factors of m. The 2 middle pops out because, well, there are 2 subsets of those prime factors corresponding to all the terms in that inclusion-exclusion sum.
Okay, so it's directly tied to how many primes you're using in your sieve.
Right. And here's where this basic sieve hits a major wall, as the sources point out very clearly.
Oh.
If you try to use this sieve to actually count primes up to x, which means sieving out by all primes up to square.
Right, because any composite number less than x must have a prime factor less than or equal to, correct?
So you set m to be the product of all primes up to square.
Okay.
But then omega m is just the number of primes up to square, which we call sk.
Makes sense.
And the problem is that error term. It grows way too fast as x gets large. It completely swamps the main term you calculated.
Ah. So the simple sieve, while it's a neat idea, it just isn't precise enough. It can't give us sharp estimates for primes in specific ranges. If you use all the primes up to the square root, the error explodes.
Exactly. It shows the limits of purely combinatorial methods when you push them too hard. This failure really highlights why we need much more powerful techniques.
Which is where analytic number theory comes in, right? Bringing in the heavy machinery from complex analysis.
That's the ticket. The sources point to Dirichlet series as being fundamental here.
Okay.
A Dirichlet series is basically an infinite sum. It looks like some fn_sq. Here, fn is some function telling you something about the integer n, and s is a complex variable.
And the magic comes from connecting these sums to products involving only primes.
Precisely. If the function fn has a nice property called multiplicativity, meaning deptim fm, when m and n have no common factors, then its Dirichlet series can be rewritten as what's called an Euler product.
Which looks like?
It's a product over all primes, prod p, 1 plus fpps plus fp2 plus dots. This is this profound link between number theory, the primes, and complex analysis, the variable s.
And the most famous example is the Riemann Zeta function, Zeta.
Indeed. Zeta sum 1 n zel. That's the Dirichlet series, where the function fn is just 1 for all n.
Simple enough.
And for complex s, where the real part is greater than 1, it converges. And it equals that beautiful Euler product, prod pic. And the sources make this really strong statement. They say the zeros of the zeta function, the values of Nax, or Zeta's Allardas, are intimately related to the distribution of prime numbers.
This is the third crucial nugget. It's really the core idea. While it's hard to explain exactly how without diving deep into the complex analysis.
Give us the gist.
Okay, think of the location of these zeros in the complex plane as encoding deep information about the irregularities, the fluctuations, and how primes are distributed. The very fact that zeta has no zeros on the line where the real part of s is 1, that's actually equivalent to the prime number theorem being true.
Wow. Okay, so the zeros are like fingerprints of the prime distribution.
Yeah.
Their positions tell you about the fine details.
That's a good analogy.
Yeah.
Their positions dictate the fine-scale behavior. Now, to study primes and specific arithmetic progressions, like, say, primes ending in 1 versus primes ending in 3, mod 4.
Right. Mathematicians generalize the zeta function using things called Dirichlet characters. We denote them Tucker.
These are functions that capture properties related to modular arithmetic, like is a number 1 mod 4 or 3 mod 4, stuff like that.
Exactly. They pick out numbers belonging to certain congruence classes, and they lead to Dirichlet L functions, sum, Schig's, and Tuggelis.
So these are like cousins of the zeta function, each tied to a specific arithmetic progression.
You can think of it that way. They also have Euler products, connecting them to primes within those progressions.
And let me guess, just like the zeta function, the zeros of these L functions are key to understanding primes in those specific progressions.
Absolutely. The location of the zeros for a given Dirichlet tells you how smoothly, how regularly, the primes are distributed within the arithmetic progression defined by that character. Understanding the zeros, especially those potentially near the line re-S1, is critical for getting strong results.
Okay, and here's where it gets really interesting, connecting to the recent news. This brings us to Zhang's work, which the sources discuss, particularly related to something called the Landau-Siegel zeros conjecture.
Right. This is a deep, quite technical problem. Landau-Siegel zeros are hypothetical zeros.
Hypothetical, so we don't even know if they exist.
Exactly. They might exist for certain Dirichlet L functions specifically, those linked to real characters, and they would be troublingly close to the point S1 in the complex plane.
Why is that troubling?
Well, their existence, if they are there, is a major obstacle. It prevents us from proving strong, uniform versions of the prime number theorem for arithmetic progressions. It messes things up badly.
Because a zero really close to S1 would mean the L function itself gets very close to 0 near 1, which somehow disrupts the expected distribution of primes in that sequence.
Precisely. It creates unexpected biases or irregularities. Now, the gold standard, the extended Riemann hypothesis, ERH,
That's the one that says all zeros of all these L functions lie neatly on the line Rietz.
that's the one. If ERH is true, then there are definitely no Landau-Siegel zeros near 1. But proving ERH is, well, incredibly hard. Nobody knows how. The Landau-Siegel zeros conjecture is specifically about ruling out these potential bad actors near S1 for this specific class of L functions.
Okay, so what did Zhang's work, as reported in our sources, actually achieve regarding these elusive zeros?
So the sources discuss Zhang's, quote, latest paper about the Landau-Siegel zeros conjecture. And they're quite clear it's explicitly mentioned that the result he proved was strictly weaker than the non-existence of zeros. He didn't prove they don't exist near 1.
Okay, so not the full conjecture. And the sources noted there was some initial confusion. Some people thought he'd proved it.
Yes, exactly. There was some misreporting mentioning Stephen Strogatz, for instance. The sources clarify that the result, while not proving non-existence, was still strong enough for many of its interesting implications.
How so? What does strong enough mean here?
Well, one key aspect, as explained in one source, is that by getting a sufficiently strong bound on how small the value of 1 Waller's-Chi can be, and also bounding its derivative near S1, you can effectively prove that there cannot be a zero within a specific region close to 1.
Ah, so his work helps carve out a guaranteed zero-free region near 1, even if it doesn't eliminate the possibility entirely.
Exactly. And the sources report that Zhang's result provides a substantial improvement on previous bounds related to 1-1. So, while it doesn't solve the full conjecture, it makes significant progress. It establishes a larger region near 1 where these problematic zeros cannot lie.
And that has real consequences for theorems about primes in arithmetic progressions.
Yes, it strengthens those theorems. It's a really powerful step forward using very deep analytic techniques.
It's just fascinating how proving things about these abstract zeros translates directly into understanding where concrete prime numbers show up. Now, beyond L functions, the sources kind of touch on a whole arsenal of other advanced techniques used in this field.
Oh yeah, analytic number theorists have developed an incredible toolkit over the years. The sources mention more advanced sieves, for example, much more sophisticated than the basic Legendre one we talked about.
Like Brun's sieve,
Yes.
Selberg's sieve.
Exactly. These use much more complex weighting schemes, clever tricks, to get better bounds on the sizes of sets with certain prime factor properties. They get around some limitations of that simple inclusion-exclusion.
The Bombieri-Vinogradov theorem was also mentioned. Sounds important.
It is. It's a cornerstone result in the field. It gives a powerful statement about the average accuracy of the prime number theorem for arithmetic progressions.
On average, meaning?
It essentially says that if you average over many different arithmetic sequences like primes mod 3, mod 5, mod 7, etc., up to a certain limit, the primes are distributed very regularly. Almost as well as the super strong extended Riemann hypothesis would predict for each one individually, provided you don't look at moduli that are too large relative to x. It's a kind of substitute for ERH in many applications, especially involving sieves. The sources even call it a form of axiom 3 for sieve methods, making them much more powerful.
And there's also something called the large sieve, different from Brun or Selberg.
Yeah, it's another versatile and powerful tool. It provides bounds on sums that involve many different exponential functions or characters simultaneously. It's really useful for problems where you need to understand distribution properties across many different sequences or sets at the same time.
And finally, the sources just sort of alluded to methods like the circle method and bilinear forms.
Right. These are deep analytical techniques, often used for tackling problems about representing numbers as sums involving primes. Think like Goldbach's conjecture trying to show every large even number is the sum of two primes.
Or finding long strings of primes in a arithmetic progression.
Exactly. Chen's theorem, which got close to Goldbach, used these kinds of methods. They often involve analyzing complex Fourier series related to primes. It's heavy stuff.
So it's really clear that understanding primes, especially their finer distribution, requires this whole ecosystem of complex analytical machinery. Often focus on the behavior of these zeta and L functions, and crucially, their zeros.
Absolutely. These tools are essential precisely because the simpler sieve methods hit that wall we discussed, and the sort of pseudorandom nature of primes is deeply tangled up with this underlying analytic structure.
But, despite all these powerful techniques and recent achievements like Zhang's work getting closer on Landau-Siegel, it still feels like the deepest patterns and puzzles about primes seem to escape us, as one source put it.
That's very true. I mean, the questions that really motivated a lot of this work in the first place, like proving the twin prime conjecture, or whether there are infinitely many primes of the form, $2 plus Offie, that's another Landau conjecture, they're still open, still unsolved.
And even more subtle things, like that Chebyshev's bias you mentioned earlier, the observation that primes equiv 3 p mod 4 4 seem to slightly outnumber primes equiv 1 p mod 4 4 for many ranges. That's still an active area of research, right? Understanding why.
Exactly. And the sources mentioned work on both small gaps between primes. How close can consecutive primes actually get? Zhang's earlier work made huge progress there, too.
Right, the bounded gaps result.
Yeah. And also large gaps between primes, how far apart can they be? These are active areas where all these sophisticated tools are constantly being refined and applied.
Okay, so let's try to recap our journey through this deep dive then. We started with the simple mystery of primes and that foundational insight, the prime number theorem showing their average distribution follows a predictable rule.
Then we saw how basic sieve methods, while intuitive, just aren't precise enough for the detailed questions, revealing why we need these more powerful analytic techniques.
We plunged into that world of complex analysis, understanding how Dirichlet series, L functions, and especially the location of their zeros, are fundamentally linked to how primes are distributed both overall and in specific sequences, like arithmetic progressions.
And we highlighted how recent breakthroughs, like Yutang Zhang's work related to bounding values near S1, to constrain those problematic Landau-Siegel zeros, represent real significant progress in overcoming long-standing obstacles, even if they don't completely solve the ultimate conjectures yet.
We also got a glimpse of the wider toolkit advanced sieves, Bomburi-Vinogradov, the large sieve, the circle method, quite an arsenal.
It really is a field where incredibly abstract mathematical theory complex functions, zeros, is directly applied to uncover the hidden, non-random structure within this sequence that looks, at first glance, almost chaotic.
So what does this all mean for you, the listener?
Well, it means that the primes, those simple building blocks, they're just full of surprises. And mathematicians are using this stunning array of techniques, everything from basic filtering logic to the deep geometry of complex functions and their zeros to try to map out their landscape. It's this relentless effort to find the hidden order.
And here's maybe a final thought to mull over, picking up on that tension we talked about between randomness and structure. We've seen how the idea of primes behaving like random variables can be a useful intuition, a good starting point.
Right, the Kramer model sort of picture.
But we also saw their distribution is rigidly dictated by deep analytical properties, especially those zeros of zeta and L functions, and it's also constrained by those simple local obstruction, those basic arithmetic rules.
So consider that interplay. How much of the prime number's behavior, their patterns, their gaps, the biases, is truly like random chance, governed by probability? And how much is completely predetermined, locked in place by these deep deterministic mathematical structures hidden away in the complex plane?
That's a question that definitely keeps mathematicians busy, and it's certainly something worth thinking about. Thanks for joining us for this deep dive.
Until next time.